Okay, welcome back everyone. In this video we're going to be talking about a very important effect that occurs with all waves, and we'll look at it in the context of sound waves. So we're doing with the Doppler effect. So first, a definition. The Doppler effect is basically a change in the perceived frequency of a wave. And it's caused by relative motion between the observer of a wave and the emitter of a wave. So the important thing to note here is that it's relative. So if the observer is making a sound, and I guess that would make them the emitter, but if they were running away from a source of sound, or if a source of sound was moving towards you, it doesn't really matter. It's kind of the same idea. Now, mathematically, the way that this works is that the frequency that the observer measures is equal to the frequency that the source emits times a fraction. And there's a bunch of speeds we have to keep track of. We have the speed of the wave plus or minus the speed of the observer, and that's divided by the speed of the wave minus or plus the speed of the source. And I'll be giving a good example of this in the next video, but what is the deal with those plus and minuses? Basically, if something is moving towards you, you're going to use the first or the upper ones, the plus and the minus. So if two things, if two objects are moving towards each other, then what you end up using is a plus and a minus. And that makes the numerator larger and the denominator smaller. So the end result is that the frequency is going to increase. Now, if two objects are moving away from each other, then you're going to use the opposite, minus and plus. This makes the numerator smaller, denominator bigger, and the frequency will become less. Okay, so that's enough about the equation, but what is it? So, oops, that's my sound demo. Okay, so here's an applet, and what we have on the upper right is basically a ratio between the speed of the wave, the speed of the source and the speed of sound itself. Okay, so if I just put a dot right here, now I've made it go at about 60% the speed of sound. So if I pause this, what you can see is that over here out in front of it, the lines are closer together. So these are the individual waves. And so the frequency of those is greater. They're going to hit you more often. Now out here behind it, the frequency is less. And that's the basic idea behind the Doppler effect. Now if I just do a dot in the center with no speed, you can see perfectly concentric circles. And then if I drag to, let's just say, that was close to 1, notice how they're bunching up at the front. So the object is moving just as fast, pretty much, as the waves it's sending out. So that's kind of important. Now what happens if the object goes faster than the waves that it's emitting? Well, then, notice my arrow turns red. We'll just do a little bit faster. Okay, so that's about 4/3. So notice what happens is that as the object moves forward, it creates this cone shape. So this is known as a shock wave. If you're over here, for example, then this line of waves is going to hit you all at the same time. And here's a cool picture of it. It went right here. Okay, here's a plane creating a sonic boom, and you can see that cone shape. There's actually two, one near the cockpit and one near the tail of the plane. So it's really interesting to think about what's actually causing this visible cloud if sound is just something that occurs in air. Why is there something that we can see? So we'll talk a little bit about that in class. And finally, going back to the applet, what if I go much faster? What happens to this cone? So let's say I go 3.5 or 3 1/3 times the speed of sound. Whoops, let's do that one more time. Maybe not quite as much. So what you can see is that because it's moving faster, these sound waves have not had as much time to expand, and so the cone is actually narrower. And you can calculate the speed of an object by the angle of the cone. The narrower the cone, the faster it's traveling. So that's kind of cool. And finally, this explains the sticker on my door. The sticker on the door to my office, which says if the sticker is red, I'm sorry, it's a red sticker, and it says if this sticker is blue, you're going too fast. And what that refers to is red shift and blue shift of light. And so as you know, blue light has a much higher frequency than red light. So if you are traveling towards something at a very high rate of speed, the light from it will actually look more blue. So we actually see this with the sun, we see this with other stars, and so even though I messed up the joke, that explains the bumper sticker. So the faster you travel towards something, the more blue it will appear. So in the next video, I'll show you a quick example of how to solve a problem using the Doppler effect.